the session. This audio-visual session is being recorded and will be posted later online to the My TCC Blackboard page for this class under the section on the left entitled Recorded Presentations. Today on the schedule, it's February the 2nd, we're going to be covering our Module 4 on Inter-VLAN routing. We talked last time about creating VLANs on switches, and then when you did the lab, you found out that, for example, the switches were on one VLAN and the two PCs were on another VLAN, and while the switches could ping each other and the PCs could ping each other, there was no way the switch could ping a PC or a PC could ping a switch. And that was because there was no router in there, because routers by definition connect networks together, regardless of whether we're using VLANs or not. So we're going to add that step in and talk about that today and see how we bring in a router and create inter-VLAN routing and do it very efficiently using that same trunking cable that we connect between one switch and another switch. That trunking cable is a special type of connection that goes from a switch port to another switch port that commingles all the VLANs on one physical wire. So we can do that with a router and use one single Ethernet port on a router and have it route back and forth, because we can configure the router to understand the trunking protocol and have it trunk back and forth between those particular devices. Okay, so let's get to the PowerPoint presentation, and I'll share that in 1 second. That'll be right up. So inter-VLAN routing operation. So we use VLANs to create different layer 2 networks, different broadcast domains. There were a number of reasons that were presented. We might be different departments or different organizations or different floors of a building. So anyway, if you have create VLANs, one host in one VLAN can't communicate with hosts in another VLAN. So our switches could not ping the routers, and our routers could not ping the switches. So what we're going to do is look at the ways that we can connect these two together using some sort of routing type to come in there to route them back and forth. There's 3 ways we'll look at. A legacy method is, well, when we only had 2 VLANs in that last lab, we had the VLAN 99 for the switches, and we had the VLAN 10 for the PCs, the employee PCs. And our routers have 2 Ethernet ports. So we could simply run a wire, 2 wires from the router to plug one into a port that's been assigned to VLAN 10 and plug another into a switch port that's been assigned to VLAN 99, and that would work okay. But we can only do 2 VLANs. And if you have more than 2 VLANs, you either have to buy a more expensive router that has lots more Ethernet ports, or what we're going to do is use the second option, which is router on a stick, in which we're going to run a trunking cable up to that router, just one wire, just to one port of the router. And we're going to configure the router to route back and forth. We're going to configure the router so he understands the trunking protocol, and he can pick up a VLAN 10 trying to ping a VLAN 99 device, and he'll route back and forth between those and send them back in and out through the trunk using the proper tagging on the trunks. This works okay for small to medium-sized networks, which CCNA sort of defines up medium-sized networks as up to about 200 to 250 devices. If you're in a larger organization with thousands and thousands of users, typically this is done using, I don't like this term, a layer 3 switch. Switches, Ethernet switches, are layer 2 data link layer devices. They make their porting decision using Ethernet frames and create a virtual circuit between one port and another port. The electronic technology has gotten so fast and good that a lot of layer 3 routing functions have been put in what we used to call these layer 2 switches. So these bigger chassis-based switches typically have a blade that will plug in with maybe 48 Ethernet ports, and another blade that plug in that maybe had fiber optic ports, and then it has a module that plugs in that has a router. It's essentially a router on a printed circuit board. Now, the Cisco marketing guys don't call it a router, they call it a supervisor module, but it's a router. It's programmed and configured exactly the same way a router is. So layer 3 switches can do some, our switches that we have in the lab can do a little bit of static routing. They can't do like OSPF or dynamic routing. But the bigger switches that are more than $500, and I'm talking about 5 and 6 figure values, $50,000, $1 million, they have the capability that can do this stuff. We'll look briefly at that. For the purpose of CCNA, we're really worried about routing on the stick. So here's our legacy method. We have a switch, and we're going to run 2 wires up to the router, and they're not going to be trunking. They're simply going to be access ports. And we're going to plug one to the G000 port and plug another one to the G001 port. And in this case, they've configured the network to be VLAN 10 as the third octet of the IP address is a .10. VLAN 20, the third octet of the IP address is a 20. And the router can be configured to route back and forth because routers, all we have to do is configure the IP address on those 2 gigabit ports, and automatically he will create a routing table and he'll route back and forth between those 2 directly attached networks. No static routing required. No dynamic routing protocol required at all. Cisco routers automatically route between all their directly connected ports. But the problem with this is we're limited to just 2 networks. So if we want to do this in a more modern, in an environment where we have more than 2 VLANs required, we're going to run out of ports on the router. And you don't want to just buy a router that has 12 Ethernet ports on it. Those are very expensive. So it's not scalable at all. So the router on a stick method is we're going to extend this trunking concept, which is already going between the switches. We have that fast Ethernet port 0, 1 on both switches. We're connected together in our last lab, and we configured it to be a trunking port. And it added that VLAN tagging to all the standard Ethernet frames that go back and forth between the host machines. Host machines don't understand VLAN tagging. Got to strip the tag out and put it back as a regular Ethernet frame, or they will not understand it. But switches and routers can't understand tagging. We just have to configure them and tell them to do so. So we're going to go to a Cisco router, and we're going to configure one of those Ethernet ports to send and receive trunking information. And we're going to connect that to one of the trunking ports on one of our layer 2 Ethernet switches. And then we're going to use a new concept called the sub-interfaces, because there's going to be 2 or more broadcast domains with different network addresses. Maybe one will be .10, maybe one will be .20, maybe one will be .30 or .99. And we're going to configure sub-interfaces to identify those routable VLANs, because it's only one physical interface. Now, sub-interfaces are a logical way of creating a different many network addresses that are in different networks on one physical port. And this is not a new idea. If you have, like I have if you have one of these cheap $7 a month web services where you can put up your own website, you don't get an entire computer to do that. So it's been possible for many years, even since Microsoft Windows NT Server, which has been around since 1995, had the ability to put 6 different IP addresses on one physical Ethernet adapter. So that way you could run an NT server and you could have 6 different customers that you were leasing an internet service provider web hosting service to those. So we're going to do the same sort of a thing with our Ethernet interfaces. We're going to create sub interfaces and make one of them correspond to the VLAN 10 network, one of them correspond to the VLAN 99 network. So they're software based. And there's only one single physical Ethernet interface, only one real thing with wires. We're going to configure these sub interfaces logically on the router using the iOS software. Each sub interface is going to have its own particular IP address and its own VLAN assignment. And we're going to do something that just makes good sense. If we have VLAN 10 and we have made that maybe the 192.168.10. something base network, we're going to make that sub interface number 10. So these things sort of correlate and line up with each other. It just makes it easier to come back and troubleshoot it later. So when a VLAN tag traffic goes into a router, it's going to go in the software logically to that VLAN sub interface. He'll look in his routing table. If we look in the routing table, we'll see multiple entries for each one of these logical software sub interfaces, as if they were actual physical interfaces. Then the router will make his forwarding decision. He'll look at the destination network, determine if he has an exit interface, an egress interface that corresponds to that. and he'll go and forward that IP packet out that particular subinterface. And then it'll be tagged, go through the trunking wire back to the switches, and all of those devices that are on that VLAN corresponding to that IP subnet broadcast domain, they'll be able to receive that data. So you'll be able to ping back and forth between, for example, the switches and the PCAs and PCBs will be able to ping back and forth between each other. Now we can do this with our Cisco switches that we use in the laboratory, about $500 a piece, about street price. The price of the routers that we use is about $1,000 a piece. This works well for a small or medium-sized company. It works up to about 50 VLANs. Once you get beyond that, it starts to become inefficient, and you need to step up to a hardware dedicated, what they call a layer 3 switch or multi-layer switch. So, and we're talking in the neighborhood now of $50,000 switches on up to $1 million switches that are really switches and routers, all in one chassis with plug-in circuit boards. So we're going to use layer 3 switches. This is a third method. This isn't a big company that needs lots and lots of VLANs. So this icon, you notice the icon on the screen here at the top, instead of being the router, it's that picture that looks, it's sort of like a cube, sort of like our switches are, but it's got a layer 3 interface in it. It's got layer 3 circuitry. It's got layer 3 integrated circuit functions that can do this stuff. So typically called a multi-layer switch or a layer 3 switch. I don't like that term. It's confusing to fundamental students because they have learned in the fundamentals course that a Ethernet switch is a layer 2 device and a router is a layer 3 device. Ethernet switches make their forwarding decision based upon layer 2 MAC addresses. Layer 3 devices like routers make their network forwarding decisions based upon layer 3 network addresses. So in this case, instead of a small company that uses we don't have any big, super big $50,000 switches that we can use in the lab. So in this case, in a large company, that device would be a big rack mount thing the size of a refrigerator, and it would have multiple plug-in circuit boards that had connections for maybe up to 1,000 different Ethernet devices to be plugged in. So it's going to do the same thing we're going to do with our cheap $1,000 router. It's going to route back and forth, and those two wires that form the sort of a triangle connection between the two switches near the bottom and the multi-layer switch at the top, those are going to be trunking cables that tag all the Ethernet frames and identify with the trunking ID, the 802.1q trunking protocol, it'll identify the VLAN members. So the advantages are, well, it's an advantage that comes at a cost. The switches are much more expensive, but they're much faster because instead of doing everything in software like our $1,000 routers do, they do everything in very fast integrated circuits. They're called application-specific integrated circuits. They're custom circuits that are built to do a specific job. So hardware is generally much faster than software is. There's no need, since everything is one chassis, you don't have to run trunking cables between the routers and the switches. They're all in that backplane of the box. We're not limited to one link because layer 2 ether channels can be used. We haven't talked about ether channels yet. That's coming up in a later chapter. Ether channel is a method of say, combining 4 or 5 optic cables together that are 10 gig each and getting a 40 gigabit channel. So the latency, the delay is lower because the data doesn't have to flow out of the switch to a router and then flow back to the switch again. More commonly deployed in a campus local area network than routers, and the big disadvantage is it's a much higher expense. So a company that has 1,000 or more people, they probably use this scheme. Companies that maybe have 200, 250 people, they're going to use the devices like we use in the labs. Simple $500 Cisco switches and $1,000 Cisco routers. So that's what we're going to concentrate on in this particular chapter. So here we have got, in this diagram, we have a router at the top, and we have below the same technology we've been using in our previous chapters. We have a couple of S1 and S2 switches that are linked to each other. The F01 of switch 1 goes to the F01 of switch 2, and that's been configured to be a trunking port, so you can carry all the VLANs that may happen to exist in that particular setup. We have PCA, PC1, connected to port 6 of first switch, and we have PCA or PC2, PCB, connected to port 18 of the second switch, just like we do in a lab. So what we're going to do is take that router 1, R1, and we're going to create some sub-interfaces on it. Now, physically, the trunking cable that goes from port 5 of switch 1 up to the gigabit 00/1 port on the router. That's a trunking cable, just like it was going to another switch. All the different VLANs, Ethernet frames have been tagged and identified as being VLAN 10, 20, or 99 in this particular case. And we're going to do some configuration on that router to create some sub interfaces. We're going to take that physical interface number G001 and we're going to put a dot there and make an interface, a logical software interface called .10 and .20 and .30, and we're going to correspond those to the particular IP addresses. So if we don't have any configuration on R1, it's going to be like we did in that last lab. The two PCs will be able to ping each other, and the two switches will be able to ping each other through their management interfaces. But the PC can't ping the switch, and the switch can't ping the PC. So we're going to have to go into the router and do some configuration. It's not that difficult. It's not that tough. So here's what we're going to do. We're going to create and name the VLANs. We're going to create management interfaces on the switches. We're going to configure access ports like port 6 to the first PCA on the first switch, port 18 to from S2 to the second PC, and we're going to configure our trunking ports. So here's the configuration for example. Let me turn on my little pencil here. Okay, so configuration for S2 is going to be similar to S1. So on S2, we had a device plugged into port 18. We had a PC plugged into port 18. We configured that as an access port and assigned it to VLAN 20. Then we had a wire coming between the two switches. Port number 1 of each switch is connected to each other. We configured that using my preferred configuration, switchboard more trunk, unconditionally make it a trunk. And then he created a management interface on this switch, the VLAN 99. And he also gave it the IP default gateway command, which we talked about before, in case you wanted to, you weren't plugged into that switch's network, or you want on some other network, you'll be able to log into it. And in the top portion of code, they've created VLAN 10, VLAN 20, and VLAN 99, and they've named them. So on switch 1, they'll do the same sort of thing. The only difference is on switch 1, port 6 instead of port 18 goes to the PCA. So we're going to create a sub interface on the router. This is our new, okay, that was all review. This is our new command that we're doing. We're going to type in a command that says interface gigabit Ethernet 0/0/0.10 or .20, and then we're going to go and tell him what VLAN he's supposed to be associated with, and then we're going to assign an IP address to that sub interface. Now, before this time, we've only assigned one IP address to a physical Ethernet port, maybe 192.168.1.1. But when we create our logical subinterfaces, we're not going to assign any IP address to the physical port itself. We're going to assign IP addresses only to our subinterfaces that we're creating, .10.1, .10.20.1, .30.1, .99.1, and so forth. Now, I mentioned last time when we talked about trunking that there was Cisco early on used a proprietary method of tagging the frames called ISL, Inter-Switch Link. That's been deprecated, not supposed to use that anymore. It's considered obsolete. It only works between Cisco devices. The open standard that everyone uses, all vendors support, which is supported, open standard is one that's all vendors are free to use and don't have to pay a fee for it. So this is called the .1Q encapsulation method. So 802.1Q is the IEEE specification for this. Everybody can use this. And this means that any device can interoperate with any other device. They don't have to all be made by the same manufacturer or vendor. So when we create that sub-interface, we need to tell it what encapsulation type, because the router, which is brand new, might be connected to an old Cisco switch that's 30 years old, and it's running the old inter-switch link. We might have to do encapsulation ISL instead of encapsulation .1Q. Not in our labs. We don't got any old equipment. We're going to always use encapsulation .1Q, the modern preferred open standard method for doing this. Now, remember native VLANs? Oh, you've slept since then, maybe forgot. So a native VLAN is a VLAN in which those frames assigned to that VLAN are not tagged in any way. It's there for backward compatibility with old equipment. By default, the native VLAN is the #1 VLAN. I think in our lab, we made the native VLAN the 1000 VLAN and just put it out there as a garbage VLAN that nobody could use. So when we configure them on the switches, you remember if you configured switch 1 and it was native VLAN 1000, and the second switch and the first switch started complaining frantically that the VLAN's native IDs did not match. And when you configure the second switch to match, those errors stopped. So we're going to configure our router in the same way. If we're using a particular VLAN 1000 as the native VLAN, we'll configure it on the router to be the same way. We'll configure the IP address exactly the same as before. IP space address space, and put the address in the subnet mask header. We'll repeat this for each VLAN. Now, you don't do a shutdown and a no shutdown command on individual subinterfaces. You can only physically turn on or turn off a physical wire, that RJ45 connector that's labeled gigabit 00 or whatever we have. So we're going to do a no shutdown on the physical port after we've configured everything. If we do a shutdown, all of the subinterfaces we created will be shut down all at once. If we want them all to work, we'll turn them on again. So let's take a look at this configuration. Pencil work and pencils. Okay, so now, warning, Will Robinson, in the labs that we have, they assume it's a Cisco router that uses G0/0/0 and G0/0/1. In the routers that we physically have in our lab, it's G0/0 and G0/1. If you type interface G0/0/0 on one of our routers in the lab, he'll come back with an error message. He doesn't have that numbering on his. Now, if you do this in Packet Tracer, you can simply configure a 4321 type router, and the number will match it exactly. It'll match what's in the lab. So here's the configuration. He's created the interface port, interface G001, and added the .10. And notice that the prompt has changed from config. Instead of config-if, it says config-subinterface. He's added description keyword and said, what is the encapsulate? I need to tell what VLAN number is going to be associated with this particular subinterface. So if it was subinterface.10, let's make that correspond to VLAN number 10. And the .1Q says use the standard preferred modern encapsulation type. And then we say IP address and give him the 10.1. And then he proceeds in this fashion, and he goes to interface, creates interface G0/0/1.20, VLAN 20, encapsulation .1Q 20, 20.1 IP address. And then he goes to the management interface 99, encapsulation .1Q 99, 192.168.99.1. And then he goes to the port itself. The physical port itself was G001. We're not going to do any IP addressing on this. The IP addressing is all taken care of in our sub interfaces. So he simply puts a description. Oh, this is the trunking link that goes back to that port number 5 on switch number 1, which has also been configured as a trunking port. And he does the no shutdown command. Now, the router is routing back and forth between all the different devices. You can ping from any PC on any VLAN or from a switch management port address to any other address. It will work just fine. He suggests that you go into your PCA, PCB, VMware, or if you're using Packet Tracer, make sure the configuration of those is proper. So everything should be able to ping everything else. So some verification commands we can type. We can type show IP route and see the routing table, and you'll see the .10, .20, .30, .99 interfaces in there. You can type show IP interface brief as a very quick check that you didn't forget to type the no shutdown command, you didn't create any typing errors or fat finger errors, and type 129 instead of 192. You can type show interfaces and show interfaces trunk and make sure that the trunking wires are trunking wires. Now, using layer 3 switches, this is the exact same scheme, but the router and the switch, instead of being separate devices that you plug together with Ethernet cables like we really will do in the lab, or you really will do if you do this on Packet Tracer, it's done using an more expensive chassis device, a modular device that you can plug different boards, printed circuit boards into. The separate router and switch scheme we're using is okay for maybe up to 50 VLANs, maybe up to a couple hundred employees. But for a much larger enterprise, like Tarrant County College Network, we have 4,000 employees, we have 100,000 students. We need something that's more scalable. So we use these so-called layer 3 switches. Boy, I hate these names that these stupid marketing people went to Hawaii on a retreat and drank some rum and came up, oh, let's call it a layer 3 switch. Sorry, rant mode over. So layer 3 switches are hardware based. They're much more expensive because they're doing all the stuff that like our $500 switch would do. They're doing it with actual hardware chips. Now, actual hardware costs real money. Software is free. We can do anything we want to with software. So these layer 3 switches are commonly put in wiring closets. We have them around in our building at South Campus in the business building. The building next door, the academic classroom building cluster that has 4 classrooms around a patio. There is a room in there that has a much more expensive layer 3 Cisco switch that does this distribution layer stuff. So layer 3 switches have the ability to route from VLANs, just like our $500 switches and $1,000 routers do. They can convert a layer 2 switch port to a layer 3 interface. And if you have a switch that does this, you can convert a port to either a layer 2 switch to go to a device or a trunking port, or you can make it a layer 3 port to go to maybe at least telephone line connection to the ISP or back to the home office. So this is where this term switched virtual interface comes in. A switched virtual interface is that management address we give to our $500 Ethernet switches. We say interface VLAN 1 or interface VLAN 99, and we give it a management address and we do no shutdown on that. So in one of these large $50,000 or $1 million Cisco devices, you create a layer 3 switch virtual interface for each of these subnetworks you're creating in your very large enterprise-based network. So instead of the round router at the top, we've got the square layer 3 switch, a much larger device that has individual printed circuit boards to do some of the printed circuit boards do the switching function, some of the printed circuit boards do the routing function, and it has these more expensive custom integrated circuit chips, these very large scale integrated circuit chips that do everything in hardware rather than in software. And this gives the high performance you need. What if you were, somebody like the college district where we have 100,000 students, we have this big need for performance, or you're an internet service provider. You can't get that kind of performance out of a $1,000 router. So you have to get much more expensive equipment. So we would do the same sort of thing logically. We would create the VLANs, maybe VLAN 10 and 20. We would create the switch virtual interface, VLAN interfaces, and give them IP addresses. We would configure the access ports that go to the individual PCs. And we would configure the trunking internally in this big box. We don't actually have, what we're going to do in the lab is we actually have a switch and a router, and we have to run an Ethernet cable between them to carry the trunking information. On these big boxes, these expensive 3-layer boxes, it's done in the back plane of the box. Very high speed connections, much faster than we can get with standard Ethernet cables. We would verify this in the same sort of a way. We could type ping commands and ping all the different devices in the different subnetworks. They all should be able to ping each other just fine. We can check on the Windows devices using the ipconfig command. If you use the packet tracer to do this, packet tracer does a sort of a simulation of Windows. You can type ipconfig on the packet tracer PC host, PCA, PCB, and he'll type something on the screen that looks similar to what you see on a Windows machine. And successful things show that we have inter-network connectivity. Now, if we do want to do some routing on the layer 3 switch, since the layer 3 switch incorporates all the functions of our separate $500 Ethernet switches and our separate $1,000 Cisco routers, we can do routing as well. We can do static routing, we can do dynamic routing, and we can create a port that goes to other parts of the network by, as previously mentioned, we're going to change it from a switch port, which is a device that can either an access port or a trunking port that goes to the switch, or an access port that goes to a separate PC. We can make it a switch port that maybe goes to another router or goes to a leased telephone line connection to another location. And we simply use the command no switch port. It's now no longer a layer 2 access or trunking wire. It's a routed wire. Then we can configure with an IP4 address and connect to other devices. That's sort of beyond the scope of CCNA. You're really only expected to be able to take a $500 switch or two and a $1,000 router and be able to configure those together. So using layer 3 switches, for example, we have our PC1 and PC2. They're configured to be on different subnets. We've configured the layer 3 switch to do internally in the switch. He's doing the routing. He's doing the trunking between the different VLANs. And perhaps that layer 3 switch in the academic building is going to a connection to a router, our campus router, and that's going back to the Trinity River campus where the Web Advisor server and the MyTCC Blackboard server is located. And that would complete the connection between those. Now he mentions a dynamic routing protocol called Open Shortest Path First, OSPF. That's the one routing protocol that's now currently in the CCNA objectives. And we're going to get that in the next 8 weeks after spring break. We're going to look at Open Shortest Path First dynamic routing protocol. But first, we're going to view, in this section, we're going to do a little bit of simple static routing. So on a layer 3 switch, we would do step 1, we would configure the routed port using the no switch port command and do a no shutdown and turn it on. We would use the routing, turn on routing, use the command IP routing to turn it on, configure routing, router OSPF1, don't worry about that, it's coming up next 8 weeks. And then we could verify our routing by showing the IP route command, and this shows what's in the memory of this hardware-based, very fast router switch combination. It'll show the routing tables of all the networks he knows about. Then we could verify connectivity using the ping command. Okay, let's look at some troubleshoot. It may not work. There's a lot of things involved here. The wiring could be improper. The configuration could be improper. So first of all, we're going to check the physical layer to see if the cable is connected to the wrong port. Now, if you do this in Packet Tracer, make sure you drag the right wire to connect the right port to the right port. When you come in to take the labs from me in person, I can't let you get your grubby grummies on the wires yourself. I have been known to make wiring errors. So I might need to, if you have a problem, I'll check your wire and make sure I didn't mess up a wire. We're sharing the lab with another class which uses different labs and want to make sure that the wiring is proper for you when you come in there. So let's resolve any physical layer issues with wiring. Make sure the cables are actually connected to the right port. And then we're going to check our configuration commands, our software commands, and make sure they're proper. Are we missing a VLAN? Well, let's create the VLAN. Go to the global configuration mode, VLAN 10, name, give it a name. Make sure the host machine you're trying to use has actually been assigned to that VLAN, because VLANs are a two-step process. We create the VLAN, A, and then B, we assign individual access ports to that particular VLAN, depending on what department they're in or what floor of the building they're in. So we can show VLANs to make sure which ports are assigned to which VLANs. We can show interface to switch port. We can ping to make sure they're working properly. Okay, switch trunking port issues. Make sure the trunks are configured correctly. Now, I spoke last time about I was not fond of this dynamic trunking protocol, DTP, dynamic desirable, dynamic auto stuff. I would rather not trust some protocol to do that. And I would rather just say switch port mode trunk, unconditionally make a wire a trunking port if it's going to another switch or going to a router on a stick. Or say switch port mode access if I want it to be an access port that's going to an individual PC. So we can check this with show interface trunk, or we can show the running configuration. Not mentioned in this slide is a cool command, show interface status, which in one command shows you all the interface ports on the switch and tells you if it's on what VLAN it's assigned to, or if it's trunking port, it's trunking. A combination, sort of a combination of show interface trunk and show VLAN all in one command. Very handy command. Okay, switch access port issues. Make sure that PCA has been assigned to VLAN 10, for example. PCB is assigned to VLAN 20. Make sure it's an access port and it's been enabled. Make sure the host machine is configured to be on the right subnet to match its default gateway. Because even if they're physically connected together and hearing each other's Ethernet frames, if you configure the default gateway to be 192.168.10.1, well, then that host PC has got to be 192.168.10. something else, 10 or 11. You could accidentally configure the PC to be 192.168.20, and this default gateway is 10, they're not going to be able to communicate with each other. They will ignore each other. So we can type show running configuration, show interface to switch port. We can check on the PC with ipconfig to make sure that that host PC is properly configured. On the router itself, a common mistake is when we configure those sub interfaces that they were incorrectly configured. This is why it's such a good idea to make these three values match. The third octet of the IP address is maybe .10. Make it VLAN 10, and make that sub interface G00.10, so they all line up with each other. It makes it easier to troubleshoot later. And we can check that with show IP interface brief or show interfaces. Okay, so here's some examples of some errors that may occur. So we've created 3 VLANs here, 10, 20, and 99. VLAN 10 is for the PC1 and all its neighbors. VLAN 20 is for PC2 and all of its neighbors. And VLAN 99 is for the management addresses of the switches, so they can check each other out. Okay, so what's going on here? Let's see the first problem. Missing VLANs. An inter-VLAN connectivity issue could be caused by missing VLAN. Maybe it wasn't created. Maybe it was accidentally deleted. Maybe it's not allowed on the trunk link. That was that weird command that we normally all VLANs are allowed on a trunking link, but we can block ones we don't want. If a VLAN happens to be accidentally deleted and any ports that were assigned to them, they sort of go into this no man's land. They're still associated with that VLAN which no longer exists. Now, when you recreate that VLAN, they'll come back. But if you deleted the VLAN, you need to move those host ports, those access ports over to a VLAN that works more if you intended to delete it. So we can type the command show interface. In this example, fast Ethernet 0/6 switch port, and that'll show us, well, yes, it's a access port, but look, that access mode 10 that it was assigned to, that VLAN is inactive because maybe that VLAN was accidentally deleted. And the fix for this in this slide would be recreate VLAN 10. Trunking, misconfigured switch ports. If the router port is not assigned to the correct VLAN on a router, could be a misconfigured trunking port. So in the lab, we're going to use port number 5 of the first switch to go up to the router's Ethernet port and create that link of all the trunking material going up to the router so you can do the inter-VLAN routing with sub-interfaces. So in this case, he's typed S1 on the switch S1, show interface trunk. VLAN port 1 is connected, it's trunking to the other switch, but there's something missing here. There should also be port 5 should be present here because it's going up to the router. So someone forgot to go to port 5 and say switch port more trunk and make it configured to be a trunking port. Access port issues. Let's make sure that the switch ports are properly configured. Make sure that the host PCs are in the right address subnet mask. So we can use show VLAN brief and make sure that in this case, look what's wrong with this printout of this iOS listing here. Port 6 is access port, that's proper. But look at that, here's the problem right here. Wasn't port 6 PCA supposed to be assigned to VLAN 10? So someone created VLAN 10, but they neglected the second step. They didn't go to port 6 and move it over to VLAN 10. That would fix this particular problem. The router itself must be configured properly. Now here's an example of a fat-fingered command. They went to the router and they created the sub-interfaces and they assigned the IP addresses to them. But when we do show interfaces, look at VLAN 10. We know that 1.10, it corresponds to the VLAN 10 on the switches. But when he typed the encapsulation command, he didn't say 10, he accidentally typed a second 0. And so he thinks it's VLAN 100. There's no VLAN 100 in this topology. And that's going to kill any communication between anyone that was plugged into VLAN 10 port. In this case, PCA, PC1 that was plugged into port 6 of switch 1 will not be able to communicate and ping the other devices. And I think, okay, that's it. All right then. Cool. I'm going to stop recording here.